All right, so for global atmospheric circulation, due to Earth's size and rate of rotation, the general global pattern of air circulation is broken up into 6 cells. The locations and structures of these cells are always shifting day to day and season to season. In the northern hemisphere, the bottom of the Hadley cell forms winds that blow towards the west, trade winds, and the bottom of the Ferrel cell forms winds that blow from the west, westerlies. This is why most of the weather in the United States goes from west to east. Latitude pressure zones are places where air is rising, are low pressure zones. Places where the air is falling are high pressure zones. So some of the air that rises at about 60 degrees north and south flows toward the poles, where it falls as very cold and dry air, producing polar cells. All right, so now let's take a look at Ferrel cells. Ferrel cells form around 50 to 60 degrees north and south. Air masses tend to rise, creating rainfall. Air then flows towards the equator at high altitudes, falling back at around 30 degrees north and south. Warm air at the equator rises and cools, forming Hadley cells that cause heavy cloud cover. Most of Earth's rain falls here. The cool, dry air falls at roughly 30 degrees north and south. So then for question 16, it says use the model of atmospheric circulation to explain why most of the world's deserts are roughly 30 degrees north, 30 degrees south, or at the poles. So we know that warm air at the equator rises and then cools, and that forms Hadley cells that cause heavy cloud cover. So most of the Earth's rain falls there. The cool, dry air falls at 30 degrees north and 30 degrees south. All right, so up next we have humidity and condensation. Humidity is the amount of water vapor that can exist within air changes depending on temperature. Warmer air can contain a greater amount of water vapor than colder air. Relative humidity is a measure of the percentage of water vapor in the air compared to the maximum amount the air can hold at that particular temperature. If the humidity is high, the air feels damp and sticky. The dew point occurs when the relative humidity reaches 100%. At this point, no more water can be held in the air, and droplets of liquid water or crystals of ice will begin to form. Clouds are visible because they consist of tiny condensed ice crystals or water droplets. So water vapor and temperature, dew and frost usually form late at night or early in the morning when the air gets colder than the point of 100% humidity. As the temperature falls, the air can hold less water vapor, so dew or frost forms on surfaces such as the grass. All right, so this graph right here shows water content of air at 50% and 100% relative humidity. Over here on the y-axis, we see grams of water per kilogram of air. On the x-axis, we see the temperature in degrees Celsius from negative 20 degrees Celsius to 50 degrees Celsius. And then it says, examine the graph of relative humidity compared to temperature for a city over a 3-day period. The temperature reaches a peak at about 3 p.m. on day 3. Estimate how much water vapor is in the air at that time. So we know that the solid blue line represents the 100% relative humidity, and the dashed red line represents the 50% relative humidity. So if we follow the blue curve that represents the 100% relative humidity, we see that right about at this point, it reaches its peak. Okay, so if this is the peak and it's asking to estimate how much water vapor is in the air at the time, and we know that the y-axis measures the grams of water per kilogram of air, then when we estimate, so this right here would be about like 90 grams of water, but this point is going a little bit further than that. So we can say it's about like maybe 95 grams of water per kilogram of air. So up next, we see a graph that shows the relative humidity and temperature in Chicago, Illinois for December 1st through 3rd, 2017. We know that the green is represented in temperature, okay, or the green represents the temperature, okay, and the dashed purple line represents the relative humidity. So for the y-axis, we have relative humidity in percent. For the x-axis, we see the time frame from 12 a.m. to 12 p.m. on day 1. Okay, from 12 p.m. to 12 p.m. on day 2, and then from 12 p.m. to 12 p.m. on day 3. All right, so up next we have the types of precipitation. How do different types of precipitation form? Interacting air masses. When warm air encounters a colder, denser air mass, the warm air is pushed up and over the colder air, forming clouds that may produce different types of precipitation. So over here, you have the colder air, and then you have the warmer air that's rising. So the temperature of the air high in the atmosphere is below the freezing point of water. So the types of precipitation that reaches the ground is dependent on the temperature of the air it falls through and the temperature near the surface. So frozen precipitation melts as it falls, reaching the ground as rain. Frozen precipitation melts as it falls, but refreezes on cold surfaces, becoming frozen rain. And then up next, we have frozen precipitation melts in a shallow layer of warm air, then refreezes into sleet before reaching the surface. Okay, and then the final example shows snow falling through a continuous column of cold air, never melting before reaching the surface. So we know that when the humidity is 100% and air temperature continues to drop, water vapor will continue to condense and eventually fall to the ground as precipitation. Air temperature usually drops when one air mass is lifted during a collision with another denser air mass. The form that the precipitation takes depends on the temperature of the colliding air masses. All right, so for question 18, it says, in the diagram, notice that freezing rain and sleet fall as liquid rain through the cold air mass before freezing. Use what you know about the energy of changes of state to explain this phenomenon. So we know that frozen precipitation melts as it falls, but refreezes on cold surfaces, becoming frozen rain. And then we also know that frozen precipitation melts in a shallow layer of warm air, then refreezes into sleet before reaching the surface. All right, so now let's talk about severe weather. So humans rely on precipitation for fresh water and for agriculture. But under certain conditions, severe weather can pose a natural hazard and can be damaging and life-threatening. When cold fronts collide with warm fronts, the warm air is quickly lifted and cools rapidly, and this can create storms with strong winds and lots of precipitation. Heavy precipitation can lead to catastrophic flooding. Snow blizzards can shut down towns and cities. Freezing rain can tear down trees and power lines. Hailstones the size of baseballs can damage houses and cars. In certain cases, tornadoes can spin off along these storm fronts, creating intense winds that can exceed 400 kilometers per hour and tear up everything in their paths. Fortunately, real-time ground and satellite radar monitoring can identify places where severe weather is likely to occur and provide the data for warning systems that can let people know when it is time to evacuate or seek shelter. Hurricanes and typhoons are examples of tropical cyclones, which are large, rapidly rotating storm systems with high winds, a low pressure center, or the eye, and spiraling arms of thunderstorms. Hurricanes tend to develop in tropical latitudes over warm water, which causes rising masses of humid air. Earth's Coriolis effect causes cyclones to rotate, taking evaporated water vapor from a very broad area and concentrating intense rainfall into a very small area. Human risks from hurricanes include wind damage, flooding, and coastal storm surges. All right, so now let's look at the paths of hurricanes near North and Central America. The map shows the paths of hurricanes of varying intensities in the Atlantic and Pacific Oceans. Note the large number of hurricanes that enter the Gulf of Mexico or come up the east coast of the United States. So it says on the weather map, draw where you expect the warm and cold fronts to be a day later. Mark the part of the map that will see a drop in temperature over the next day. So over here, we see cold air, and this right here in blue is the cold front. In the lighter blue, we see cool air, and then in red, we see warm air, and then we see the warm front. So this is showing colliding air masses. Moving air masses are often shown on weather maps with arrows. Severe storms are likely to occur where a cold air mass is colliding with a warm air mass. And then how do you think California's geographic location might limit the amount of precipitation it gets? So we know that the weather in California is determined by the high pressure area of the North Pacific Ocean. During the summer, the pressure moves northward and prevents storm tracks from traveling to the north. So storm tracks are narrow zones in seas and oceans where storm travel is driven by the prevailing winds. For these reasons, California's geographic location limits the amount of precipitation it receives. Did anyone else have any other explanations? All right, did anyone have any questions about this assignment?